In the section Integrative Computational Materials and Production Engineering (ICMPE) of the Cluster of Excellence, the scientists of the institutes IHK, Access, IBF, WZL, IPT, IKV, and IGPM research together on the development of materials. Besides plastic, the most important material of our time is steel. Being the most frequently used metallic material by far, it is also exposed to constantly growing requirements. Buildings are supposed to become larger, vehicles not only lighter but also safer, and wind turbines are expected to generate more and more energy. In fact, these are global demands. Over the last decades, steel consumption has multiplied many times over. Scientists face the challenge to guarantee an optimal balance between the required mechanical properties and material costs. These properties are dependent on the chemical composition. The prices for these chemical elements are subject to large fluctuations. To produce competitive components for industry, especially expensive chemical elements as nickel or molybdenum are substituted by inexpensive transition metals like manganese. Despite that, a loss of quality has to be avoided. Against the background of producing an ideal material, X-VipMap has been developed. One example which clearly illustrates the X-VipMap are the gears of wind turbines. Gears are the most important part of wind turbines, which are exposed to high and unpredictable loads. This contributes to wear and failure. Imagine a wind farm in the sea, far away from the coast. Such a wind turbine is exposed to tremendous environmental forces as temperature and wind load. A breakdown of the wind turbine implies a complex and expensive repair. The aim is to guarantee a long service life and high mileage, as well as a high degree of resistance. Mr. Adam is an engineer and has the task to construct such a long-life gear for one of the biggest wind turbines of the world. Conventional case-hardening steel is not adequate and there are no empirical data. Therefore, Mr. Adam approaches the researchers of the Cluster of Excellence. Ms. Schwarz is a material engineer of the RWTH Aachen University and is working in the field of ICMPE. He asks whether she can design a new steel which displays the desired properties and an increased service life. The service life of gear components depends on several influencing variables. Firstly, for the production of this type of steel, the chemical composition is essential since it defines the cleanliness level decisively. But all the other following process steps are important too, beginning with the casting and solidification. The aim is the most homogeneous distribution of elements possible, so that the component has the required strength at all places. During the forging, the slug is formed and the component obtains its form. By heat treatment, the resilience of the material is set for the subsequent machining. After machining the material, the final geometry for the component is set. During hobbing, the slug is formed into the gear wheel. During case hardening, the component is heated in a high carbon atmosphere. The carbon diffuses into the component so that the exterior layer reaches an increased degree of hardness, while the core remains ductile. That is, it maintains its required elastic features. These processes are simulated with the help of X-VipMap on the macro, the micro, and the nano level. With each process step, the material is optimized. Afterwards, the predictions made here are validated by producing and testing the material. The data of the prior simulation serve as input for the next simulation along the entire process chain. Thus, for example, the information of grain size, local internal stress, or the degree of hardness can be monitored in each step of the process. In the same way, Mr. Adams' case is approached. A simulation chain for the calculation of tooth-root load carrying capacity is developed and validated with the aid of example gears. Thereby, the ICMPE researchers created a simulation platform which is able to develop a new, optimized gear wheel with the increased life cycle for Mr. Adam. This manufacturing method represents only one section of the Cluster of Excellence integrative production technology for high-wage countries. In the context of globalization, manufacturing in Europe is exposed to a new framework. The Cluster of Excellence meets this challenge with interdisciplinary research initiatives, which are supervised by scientists from the areas of mechanical engineering, material sciences, computer sciences, mathematics, economics, and psychology. Together they face the fourth industrial revolution, which is driven by an increasing involvement of information and communication technology. This change is enabled by intelligent production systems, individual machine and control components for a more dynamic and flexible production technology, from continuous data and software solutions to holistic self-optimizing factories. The research projects of the Cluster of Excellence focus on the individualization, virtualization, integration, and self-optimization of production technology.